Let's do an example of sketching an elliptic cone. Now, when I look at this equation, I don't necessarily see exactly what I'm supposed to see, but if I get all the terms on the same side, I get 2y squared plus 2z squared minus x squared equals 0. Now, if you think about the form of the elliptic cone that we looked at previously, it had something like x squared over a squared plus b squared over, or y squared over b squared minus z squared over c squared equaled 0. But we don't have that. We have a minus x squared. Well, what this is really telling us is this is the same type of equation. It's just a rotated version. If this had been x and this had been y and this had been z equals 0, the standard version of that, this is a rotated one because the x and z's are swapped. So it's really the same type of equation, and you sketch it the exact same way. So what this tells me is what I should expect it to look like versus what it is necessarily gonna, or what the general shape is rather than what the specific equation looks like. So to do these, let's set some values. Now in the xy plane, we could think about the case where z equals 0, and then you would have x squared equals 2y squared. And if you think about what that looks like, is that kind of looks like a line, right? That's, if I rewrite this, I get y squared equals 1/2 x squared, y equals plus or minus the square root of 1/2 x squared. So y equals 1 over square root of 2, or plus or minus 1 over square root of 2 absolute value of x. So you get something that looks, generally speaking, like a line. So you have that 1 over square root of 2, so that's going to get you that's going to get you a bit of a modifier on, what the slope is. All right, but you're going to generally have something like that. Actually, the slope's going to be flatter, but that's the idea when z is equal to 0. But that's not actually that interesting of a case. Let's take the case where z equals 1. So in the case where z equals 1, now what we have is x squared minus 2y squared equals 2. So then I have x squared over the square root of 2 squared, x squared, see, that's divided by 2, yeah, that's right, square root of 2 squared minus y squared over 1 equals 1. So that's a hyperbola, right? So what we find is that when the z value stops being 0, you start having something that looks more like a hyperbola. So we want to keep that in our pocket. We'll come back to that. But let's look at the xz plane. So the xz plane is actually going to look exactly like the xy plane, right? Because these are basically the same term, just with a y and one's with a z. So you're still going to have and y equals 0, you're still going to have those lines. These still aren't as flat slopes as they need to be. They really need to be even flatter, but it is what it is. And then let's look at the case of the yz plane. Now, if x were equal to 0, then y and z have to be 0, because any number that's not 0 here is going to push this up past 0. But in general, what we find is that y squared plus z squared is x over square root of 2 squared. So what that tells me is that in the YZ plane, these are circles where the radius is a function of x. So whatever x value is there, your YZ plane is going to be circles of radius x over 2. So what does that mean? Well, I mean, that tells me that you're going to have circle here, bigger circle, bigger circle, bigger circle, right? So those circles are going to radiate out. And what these tell me is that on the actual plane, you know, on the case where z is equal to 0 or the case where y is equal to 0, you just have a straight line. Sorry. So you kind of have that circle coming up that way. So in this particular case, what you actually have is you just have a right circular cone, right? It's not, and it says it's an elliptic cone, but since these values match, it's actually a right circular cone. So you're going to have that value. Now, you might ask yourself, well, you just literally said for x values, as the x values move, we have hyperbolas in the YZ plane. And the answer is yes, of course we do. Because if you go all the way back to your like Algebra 2 trig class or whatever, the last time you studied conics, if you remember the term conic section, if we have a regular cone and if we slice it at a particular location, slices of the cone or cross sections actually can produce hyperbolas. And that's the idea here. When we start shifting those values of x and we look in the YZ plane, or rather the XY plane, we look in the XY plane at as we start shifting like if we look in the XY plane, if we look in the XY plane as we start shifting values of z, what we're going to find is things that resemble hyperbolas with how they move with the data. But in this particular case, it's just you want to draw the ellipse, or in this case a circle, and then the cone will follow from there. So this is actually one of the easier ones to draw in general.